In this code, we are solving a matrix using the Gaussian elimination. And we are going to see how it evolves from a 3 loops to a 2 loops and finally to 1 loop. Mathematically, we are solving a linear system. And our goal is to transform our matrix into an upper triangular form, meaning everything below the diagonal becomes 0. Once it's in that form, we can easily solve for the unknowns using back substitution. In the code, the 3 nested loops, in 3 loops, obviously, we are doing exactly that. The first loop, I, goes through each pivot, the elements on the diagonal of the matrix. The second loop, J, goes down the rows below that pivot, one by one. And the third loop, K, walks across the columns of the current row, updating the values. The actual math inside looks like this. Inwards, take row J, subtract it from the pivot row I, and multiply it by a certain factor. And that factor, or multiplier, is the matrix with the row J and column I divided by the matrix row and column I. This operation makes the element below the pivot turn to 0, and at the same time, we update the right-hand side, the vector B, using the same factor. By the end of this process, the matrix becomes upper triangular, and then the function backtracking computes the unknowns one by one from bottom to top using that formula. And as we can see here, the matrix is solved and we can see the results. Now we are going with the 2-loop version. The idea here is to do exactly the same math but in a shorter and more efficient way. The trick is to use the C++ type var, which is designed for vectorized operations, meaning it can add, subtract, or multiply entire arrays in one go without writing loops. In this version, we remove the inner loop k completely. Instead of looping of all the columns, we can just write that. This single line replaces the entire innermost loop. What happens behind the scenes is the same math, but the computer handles every element in the row at once. The result is cleaner code, fewer chances of mistakes, and often better performances because the compiler can optimize those vectors operations automatically. And here the same thing for the 2 loops. And finally, the 1 loop version. For that version, we are using Eigen, the Eigen library, which is specialized in linear algebra. We would need its help because it's very complicated to do those operations without any loops in the normal C++ language. So now, instead of 3 loops, we only have 1. Inside that loop, the code operates on full slices of the matrix at once. For example, this line computes all the elimination factors at once. That is, all the values of our matrix Ji and divided by the matrix II for the rows below the pivot. Then we eliminate the lower rows in one single vectorized statement. This performs the same operations as before. It's always the same operation, but now applied to the entire block of rows at once. The right-hand side vector is updated the same way. Everything that used to happen inside nested loops now happens in a single, clean, high-level command. Eigen handles all the heavy lifting internally, optimized it, fast, and very close to the way we write the math on paper. And now the same thing happens with the 1 loop using Eigen. It's always the same. And as we can see in here, with the 3 loops, it's faster than doing it with 2 loops than doing it with only 1 loop. So, to sum up, the 3-loop version does everything step by step, one number at a time. The 2-loop version does the same but operates the entire rows using var, making it simpler and faster. And the 1-loop Eigen version goes even farther. It uses matrix and vector blocks to apply all the operations at once, in a form that's both mathematically elegant and computationally efficient. So, as the code evolves, it doesn't change what it's doing because it's always the same. It just changes how it's written, from manual element by element operations to full row vector operations, and finally to block matrix operations that mirror the mathematics itself. And finally, we can see that the code also works for a matrix of 50 by 50. And obviously, we can see that it takes so much more time than with a matrix 5 by 5.